Hello viewers, welcome to this module on miscellaneous topics in specification errors. So, in this module we will look at some more issues with respect to specification errors. First we begin with the issue of nested and non-nested models. So, till now the kind of testing that we have carried out and also with respect to specification errors pertains to nested models. So, what is a nested model? As you can see, model A has y regressed on intercept and k xk, x2 up to xk, whereas the alternative is model B, where we are proposing that variables x2 and x3 are omitted. So, beta 1 then x4 up to xk. So, that means model B can be derived from model A, or model B is a special case of model A as and when the coefficients of x2 and x3 are 0. That means, when beta 2 and beta 3 are 0, model A folds to model B. So, that means model B is nested within model A. And so, the usual testing procedure is we estimate model A and test whether beta 2 and beta 3 are each equal to 0. That is a very familiar test that we have already studied. Coming to non-nested models, we see that here model C and D are not such that one model can be derived from the other. So, model C has y regressed on x variables, whereas model D has same y regressed on other variables. So, C is where y is regressed on x variables and D is where y is regressed on z variables. So, C and D are different and one model does not arise as a special case of the other. So, these are non-nested models. Another case of non-nested models may be where there are different functional forms. For example, model D, as you can see, has y regressed on z variables, while model E has y regressed not on z variables, but on logarithms of z variables. So, the functional forms are different. Again, one model cannot be derived from the other. So, these two are non-nested models. So, we will concentrate on testing of hypothesis for non-nested models. Since we have already done testing of hypothesis for nested models, we will see how to apply hypothesis testing procedures or how to develop hypothesis testing procedures in case where models are non-nested. So, there are two approaches. One is the discriminatory approach, where we use some criteria to compare between different models, and we use those criteria to select. These are called model selection criteria. So, based on those criteria, we select from the alternative models that model which gives us the best result in terms of estimation. The other approach is the discerning approach, which we will take up after we finish with the discriminating approach. So, first we look at the discriminating approach, and in this discriminating approach we have alternative criteria. Two of such criteria we have already studied earlier, namely R square. R square is given by explained sum of squares divided by total sum of squares, which is by definition 1 minus the ratio of residual sum of squares to total sum of squares. So, and R square, as we know by definition from analysis of variance, we know that R square lies between 0 and 1, and the larger the value of R square, the better the model is in terms of goodness of fit. Adjusted R square brings in a penalty factor. That means, when we increase the number of regressors, usually R square goes up. So, the econometrician might be tempted to go on increasing the number of explanatory variables, which will increase the R square, whereas those variables might not all be very relevant. So, we have a penalty factor, and this adjusted R square is defined as 1 minus the ratio of RSS to TSS, where RSS and TSS are each deflated by their corresponding degrees of freedom. So, RSS is deflated by n minus k degrees of freedom and TSS deflated by n minus 1, because we have n observations. So, therefore, total sum of squares has n minus 1 degrees of freedom. Once again, going by the nature of this criteria, larger the value of R square, R bar square, better the fit is. The third criteria is called Akaike's information criteria, or AIC, and this criteria also has at its heart, it has RSS by n. So, residual sum of squares by n, and we know that lower the residual sum of squares, better the quality of the fit. But in the process, as we said, we have applied a penalty that takes into account the adjustment of the degrees of freedom as we go on increasing the number of explanatory variables. So, what is the penalty criteria here? The penalty factor is 2k divided by n. AIC, Akaike information criteria, is given by the product of two expressions. First, we have exponential 2k by n, then we have RSS by n. For application purposes, we take the logarithm of it. So, logarithm of Akaike information criteria is 2k plus n plus the logarithm of RSS by n. So, this 2k plus n is the penalty factor. RSS by n may be small, but if 2k plus n compromises that, then we do not have a small AIC. Interesting to note, AIC is a criteria such that smaller the value of AIC, better the model is. So, here unlike R square or R bar square, we are interested in getting smaller values of Akaike information criteria. So, as you can see, we have noted here smaller the better. Another similar criteria with a penalty factor is Schwarz information criteria, SIC. The criteria is given by again the product of two expressions. The first expression is n raised to the power k by n, and the second expression is RSS divided by n. And if we take logarithm, it is k by n log of n plus log of RSS by n. As earlier, lower the value of RSS by n, better the fit is, subject to the penalty criteria. So, the penalty factor here is the first term k by n times logarithm of n. So, we have seen the four criteria, namely R square, R bar square, AIC and SIC. We will also consider two more such criteria, information criteria, namely Mallow's CP criteria and forecast chi-square. So, let us now focus on what is Mallow's CP criterion. So, suppose we have a model consisting of k regressors including the intercept, and sigma square hat is the estimator of the true sigma square. But suppose that we only choose p regressors, p less than equal to k, and obtain the RSS from the regression using these p regressors only, then we denote RSS subscript p as the residual sum of squares using these p regressors. The CP criterion is defined as the difference of two expressions. The first expression is the ratio RSS p, whereas where RSS p is the RSS from the model using p regressors divided by sigma square hat, and the second expression is n minus 2p. So, it is the difference of these two expressions, and as you can see, expectation of RSS subscript p will be n minus p times sigma hat square. So, this actually boils down to, in expectation terms, expectation of RSS subscript p is n minus p sigma square, not sigma hat square, but sigma square. So, it is going to approximately be equal to n minus p sigma square divide sigma square, which is n minus p, minus n minus twice p, which is approximately equal to p. So, those models which give expected Cp very close to p, those models or that particular model or those few models are said to be the models which we choose. So, if we plot in a line, then we choose those models where Cp is close to p. So, an adequate model will show up as a point close to the Cp equal to p line. Next we come to the forecast chi-square. We have data for a time span or observations up to a given level. Using those observations and using our estimate, we try to forecast. So, forecast means we are making predictions out of the sample. These are called out of the sample predictions. So, we have a regression based on n observations and we want to forecast it from n plus 1 up to n plus t. So, for this forecast, taking our earlier developed ideas, we can see that chi-square will be the ratio of residual sum of squares divided by sigma square hat as earlier. This follows a chi-square, but now this ei square runs from n plus 1 up to n plus t. So, our sample period is n. After that, we are making a forecast from n plus 1 up to n plus t, and the forecast chi-square as we have seen earlier is summation ei square divided by sigma square, that follows the chi-square. So, the forecast chi-square is summation ei square I running from n plus 1 to n plus t divided by sigma square hat, and that will follow a chi-square distribution as I said. And so, we use this test statistic to test whether the model has a good fit. How do we do that? So, what we do is we compare the test statistic which follows the chi-square distribution with t degrees of freedom, n plus 1 up to n plus t. So, 1 to t, that is t degrees of freedom, and we reject the null hypothesis if the observed value or computed value of chi-square exceeds the critical value. After this, we now take a look at the discerning approach. So, very quickly I am just recapitulating. For non-nested models, we have two broad approaches. One is the discriminating approach, where we compare different competing models using different criteria, namely R square, R bar square, Akaike information criteria, Schwartz information criteria, then Mallow's CP or forecast chi-square. This is one set of tests. Another type of tests are applicable, and this second approach is called the discerning approach. So, that is the discerning approach. Here in evaluating one model, we consider information from the other model also. So, we now come to once again the non-nested models C and D, where as you can see C has one set of regressors X and D has another set of regressors Z. So, how do we choose between models C and D? One approach is to integrate the two models and to form one general model where we have both X regressors and Z regressors. A good example would be where we consider models C and B each simplified with only two explanatory variables. So, for model C, we will have a simplified form where y is regressed on x2, x3, and for model D, we have similarly simplified form where y is regressed on z2 and z3. So, the integrated model or the model which incorporates information from both the models C and D, that is now defined as model F, where we have x2, x3 and also z2, z3. And by now you would have guessed that what we simply do is we estimate this model and we test whether lambda 2, lambda 3 are 0. If that is 0, then it boils down to model D. If lambda 4 and lambda 5 are 0, then it boils down to model C. So, if model C is correct, lambda 4 and lambda 5 are 0. Z variables are washed out because their coefficients are not statistically significant. On the other hand, if lambda 2 and lambda 3 are equal to 0 statistically, then we say the x2 and x3 variables are washed out. So, we retain model D, and this can be done by the usual F test. However, in this approach we need to be careful. The reason is that if the x's and the z's are highly correlated, then what happens, as you have studied under multicollinearity, if the regressors are highly correlated, then individually the regressors might not turn out to be statistically significant, whereas jointly it might give you a very significant, statistically significant result. So, as a package, all the regressors taken together explain a handsome share of the regressand, but individually it is very difficult to find out whether one regressor is actually relevant or not. So, in this case, if they are highly correlated, quite likely that one or more of the lambdas are statistically insignificant. Although on the basis of the F test, one can reject the hypothesis that all the slope coefficients are simultaneously 0. That means, as a package it is acceptable, but the individual components we are not very sure which of the components are relevant. So, therefore, when we test for the individual components lambda 2, lambda 3 or lambda 4, lambda 5, then we are not going to be very sure which one to actually accept or reject, given the nature of multicollinearity. Second, suppose we choose model C as the reference model and find that all its coefficients are significant. Now, we incorporate Z2 and Z3 elements of model 4, we incorporate both to the model, and using the F test we find that their incremental contribution to the explained sum of squares is statistically insignificant. So, therefore, we say that model C perhaps is the appropriate model, but we could have started the other way. We could have taken the frame of reference to be model D. So, if we had begun with model D as the frame of reference and then found that all its coefficients were significant, and further when we added x2 or x3, we could have found that these are not significant. Once again, this also happens due to high multicollinearity. Then again it becomes not very clear, it is not very clear whether we should take model C or model D. It depends on our frame of reference. So, the chosen reference hypothesis could determine the outcome under severe multicollinearity. So, we now take a look at another test which is called the Davidson-Mackinnon J test, is now being illustrated. Suppose we want to compare the hypothesis for model C compared to model D. So, we want to compare the hypothesis regarding model C with the hypothesis regarding model D. So, we again restrict ourselves to a simple case where model C and model D have only two regressors. So, say model D simplified has Z2 and Z3. Now, what we do is we estimate this model D and we call the estimated value using our standard notation, we call it y hat di. So, the estimated model D is called y hat di. Now, what we want to do is we want to find whether this adds any important information to model C. So, we add this di hat or y di hat as one of the regressors in model C. So, we have a model C which now incorporates the estimated yd. So, the model now becomes yi equal to alpha 1 plus alpha 2 x2I plus alpha 3 x3I plus alpha 4 y hat di plus ui, where y hat di are values obtained from the regression of the model D. This is an example of the encompassing principle once again, and using the t test we test whether the coefficient alpha 4 is equal to 0. So, if it is not rejected, that means if alpha 4 is taken to be 0, if this is not rejected, then we can accept model C, because y hat di does not add any explanatory power to the model beyond that what is contributed by model C. In other words, model C encompasses model D in the sense that the latter model model D does not contain any additional information that will improve the performance of model C. And the reverse is also true. If the null hypothesis is rejected, then model C cannot be the true model. If we reverse the roles of the hypothesis, then we can estimate model C first and get y hat C I and incorporate y hat C I into model D, and then we can test H naught beta 4 equal to 0. If we now get the result that we cannot reject H naught beta 4 equal to 0, that means if we say beta 4 is equal to, actually statistically it is 0, then there is no point in incorporating y hat C I. So, then we choose model D over model C. So, these are, my dear students, some of the tests in the discerning approach. Here also we have 4 possibilities, and you can see the column headings are: do not reject alpha 4 equal to 0, reject alpha 4 equal to 0, whereas the row headings are: do not reject beta 4 equal to 0, reject beta 4 equal to 0. Accordingly, there are 4 possibilities where we can either accept both C and D, which makes it bit difficult to choose, or we can reject both C and D, which is also equally difficult in case of choice, or we can have some two good results where in one case we accept D, reject C, the other case we accept C and reject D. So, dear viewers, that brings us to the conclusion of this last module on this MOOC course in econometrics on miscellaneous issues pertaining to specification errors. We hope you have enjoyed this course on econometrics, and we request you to go again through the academic script and come back to us with whatever clarifications you require. We also hope that you participate in the examination process, and we are sure that all the participants would come out with flying colors. Thank you and goodbye.